Okay, so today we're going to be reviewing the science portion of the core EC through 6 exam. We're not going to get through all the competencies because there's a lot of information. So I was able to get through 10 of the 18 today. Okay, so that's our goal. So there is a review. I don't know if you've already seen it, but let me share my other screen with you. So there is this review that you may have, that you may see or that you may have to do. Can you see my Word document?
Yes, ma'am.
Yes.
I've actually
Okay.
been working on that.
Oh, okay, great. So this document, right, you click on the link and it's going to take you to the competencies, which is this, well, it's not the competencies, but it'll take you to like the overview of the exams. So when you go in there, you would go to the core subjects EC through 6, and then you would click down where it says preparation materials, and then you would go to the overview and exam framework. And here is where it's going to give you all of the competencies that are going to be tested on this exam. And so if you'll notice, it's got the competency as well as those descriptors in there. Let me find the science. There we go. And so in studying, when it comes time to studying, because it's going to be a while till we have another review for another section of this exam, you would be focusing on what these competencies are, and that's what you're going to be studying, and that's what you'll be inputting into this document. So for today, we're going to be going through competencies 1 through 10. And so I'm not going to say which descriptor it applies to, but for the most part, you should be able to figure that out based on like what the topic is. So like for this first one, this one's kind of chunked together. So the first couple competencies are more of, you know, procedures and, you know, kind of just like in general types of things. But as we get further down into the actual content, it's going to be more specific. So like you'll clearly see like descriptor A is, you know, conservation of energy or something like that. Okay, so you can fill it in on this document if you choose, or of course, you know, you can take notes however you'd like. Okay, so let me share my screen again. All right, so we're going to be using a Nearpod today, and so the code you should have already gotten in there. So we'll have some activities periodically just to help you kind of process that information, okay? So the science exam, the science portion of the exam, it does have a total of 18 different competencies. The first couple ones, like I said, they're kind of more general, you know, things that you should know about science in general. But with science, you should always create a safe environment. You know, there's proper protective equipment that should be used, such as aprons and goggles. And you also want to be careful with any hazardous substances that you might be working with. So for the EC through 6, you more than likely won't be working with any of that stuff, you know, until you get to probably like 4th or 5th grade. And so in general, right, we just want to make sure that students understand that the areas should always be kept clean, you know, everything should be disposed of properly. And so when we hear the term chemicals, right, we think of like, you know, really dangerous chemicals, but in the science room, a lot of the chemicals that are out there are actually like household products. You know, like vinegar is actually an acid, so that's something that you'll use pretty often. Baking soda, you know, just simple things like that. But with those, you still want to make sure that you're careful. Whenever you're handling organisms, and that's living or dead, you want to make sure that they're always handled with respect and care, and that's something that you want to teach your students to do as well. You know, even in the low grades, it's always about being careful and treating them with respect, because again, as they get through the grades, right, in high school or, you know, in middle school, they may be actually like dissecting, you know, like dissecting a frog or something. And so it's just making sure that they understand, you know, that these are organisms that we're learning from, and it's not something that you can mess around with. You always want to review those safety procedures with students, just so they understand that when it comes to science, right, it's not like we're just in the regular classroom, but there are procedures that we have to follow. And the higher grades, you may also have to provide a safety contract for parents to sign. So in the middle school and in the high schools, the science teachers will always give a lab safe, like they'll go over lab safety that first day, first day or two, and they'll always give out a safety contract for parents to sign and for kids to sign so that they understand that this is serious, like it's important that they're careful. And then, like I mentioned, most of the chemicals that will be handled in the classroom, right, they're just household products, but we still have to be careful of things, getting in their eyes. And so it's, on their clothes, some things can stain clothes like bleach, right? So you want to make sure that you always just kind of maintain those lab safety standards. And so something that they do mention is, even just having like a lab safety poster, something that you can just refer to. And of course, in the lower grades, right, if they just see it with pictures, that's going to be helpful. So when it comes to scientific tools, there are a variety of science tools that are out there. And, I'm sure when you were in high school, right, you used a beaker, you used a triple beam balance, right, all those. But when it comes to a science in the elementary grades, we've got to understand that some tools won't be introduced until they get older, and again, it has to do with that safety aspect and whether the students are able to actually utilize it the way it should be used. So for example, first graders are not going to use a microscope, right? And one of the main reasons is because microscopes are really, really expensive. And so you want to make sure that the students understand how to use it and that they literally have like the dexterity, to be able to manipulate and handle them. So for them, they might be using like a hand lens, so like a magnifying glass. So that would be something they would use. But then when it comes to, in the upper grades, like fifth graders, they're going to use graduated cylinders because they're going to be able to actually read them and measure them, but to measure liquids. But for kindergarteners, right, in the lower grades, you're just going to give them a cup, so it's not about measuring, but it's just about using the tool to move, things the way they should be moved. So it's not like, okay, you're going to move the water from here, use your hands. It's like, no, there's a tool that we use to do that. And so there's actually some charts. I don't know if you have this textbook. I know some people purchased a book to help them study. So this is kind of the one that we utilize as well. But in there, it provides like a spreadsheet that kind of shows you based on the TExES where it is that certain scientific tools are going to be introduced based on grade level. So that kind of also gives you a general idea as to where that would be. But I guess the most hazardous things, that we would be working with would start like in fifth grade, and those would be like hot plates, burners that actually have a real flame, beakers that are made out of glass, flasks, those are made out of glass, and test tubes. So you don't want to mess with those with the younger grades because if they drop them, they break them. That's a hazard. They can get hurt. And so in the science, in science in general, they always use the metric system. So you want to make sure that you understand how to convert within the metric system. So we never use inches. And that's the thing when it comes to rulers, right? You may have rulers that are going to be measuring in inches because that's what we use here, in the United States. But there's always going to be the side that has the metric system. So never anything English system, it's always going to be metric. And so for the conversion chart, this is just a kind of little example of how you would convert, but the metric system is very simple to convert because you would be basically just moving the decimal, over in order to get to where you need to go. And a simple way to memorize, like where you would go is this mnemonic device here. So King Henry died by drinking chocolate milk. So the King stands for kilo, the Henry stands for hecto. So that's just kind of a way to remember that. So for example, if I was converting, if I had 10 centimeters and I was trying to convert that to decimeters, I'm moving one place to the left. So I would literally take my 10 and I would move the decimal point one place to the left and I would end up with 1 decimeter. So that's how the conversion works with the metric system. And that would go for anything, right? So there's, there's meters, there's liters, there's grams, and they all use that same, those same like prefixes to them. So you can convert anything just by memorizing this mnemonic device. So in science, they're also going to use these terms precision, accuracy, and error. And all of these things that we're going over right now, it's something that's common to science in all the grade levels from EC all the way through 12th grade. But of course, they're going to be used to a higher level as the students get older. So when we talk in the English language, we talk about being precise and we talk about being accurate, and we use them to mean the same thing, right? But when it comes to science, there's a difference in what those terms actually mean. And so a lot of times they'll use a diagram like this to explain what those definitions are. And so, when explaining it to your students, this is something that you would use too. But precision basically just has to do with how close your measurements are to each other. And so that means that you're doing the process the same way, every time. And so with science, we always want to make sure that measurements are as accurate as possible to guarantee that our data is valid. So it's not a matter of, looking at a graduated cylinder and saying, that's about 3 millimeters, or 3 milliliters. It's like literally looking at where the meniscus is and reading that is 3.1 milliliters, So in science, it's very important that we use those, accurate measurements. And so accuracy has to do with how close the measurement is to the true value. And so, there may be instances where a student is, they're doing, maybe they're measuring with the graduated cylinder, and every time they measure the thing, they're getting the same value, but they're not reading it right. So they're being precise in that every time they're reading it the same way every time, but you have to teach them, no, like we read it at the bottom of the curve, that's where you're going to take the measurement, and that would be accurate, like that's the correct answer. So you can be accurate but not precise, you can be precise but not accurate, but just so that you understand the difference between the two. So precision, in this case here, if they're all together, that's precise, but notice none of them hit the bullseye, so they weren't accurate, right? And this one over here, they were all together and they were all in the bullseye, so it was both precise and accurate. When it comes to talking about error in measurements, there's a lot of things that can cause discrepancies. So sometimes just us as individuals, right, humans, we make error. Maybe our eyes are not, quite looking at things correctly. Maybe I didn't, put the balance on a level table. Just little things like that. When I'm transferring my liquid, I spill some. So human error can cause differences in what we get. There's also like mechanical errors. So maybe the triple beam balance isn't like it isn't balanced itself, or there's something wrong with it, so it's reading the measurements wrong. But if errors are always going to happen in science, like we're never going to do an experiment and get an exact replication of what somebody else may have done. It's always going to be slightly off just because of that. Okay, so competency 2 has to do with history and the nature of science, and then the process and role of scientific inquiry. So something that we want, that you should know, right, and that our students should understand is that science is not fixed, but it's very dynamic. And so, when you think of, I don't know, like history, or you think of math, it's like, there's this definition and this is exactly what it means, and with science, it's kind of like, wow, we have data to show us that this is what we know now based on the data that we have now, but that could change in the future. And so science is very dynamic because we're always learning more. Technology is always advancing. And so, stuff that you may have learned in high school, may be a little bit different. I know when I was in high school, we only had a certain number of elements, and now we have more, so things are always going to be changing. And so throughout history, there have always been truths, right? Things that people believed. And with the use of science, they were able to look at those observations and test them. And using data, they were able to derive new explanations. So like, for example, thinking about spontaneous generation. So, way back in the day, they didn't understand this idea of or they had this idea of germs, right? And they thought things could just like randomly grow. But based on, experiments, they were able to test it out, and they realized that they're not just like coming out of nowhere. Like there are cells there, they're just so small that we don't see them. And so that kind of changed, that idea, which, led to advances in other things. But over time, there's been, ideas with religion, or ideas with culture, and they've been tested, and through science and observations and experiments, we've been able to show otherwise just based on data. And so with students, what you want to do is you want to make sure that you engage them in the process of making observations. So science isn't just about, talking about it and, showing them presentations, but it's really about having the students engage in these things so that they can actually, they can see it, because for kids, they've already got this idea, in their heads of the world. And so we want to make sure that we show them, like, this is something that happens and it goes against like what they think, right? And so that's kind of how we can show them new things and how we can teach them. So some important science concepts that you need to know in terms of history of science are the cell theory. So that was kind of like what I was mentioning with that like spontaneous generation. So everything is made up of cells. And so if something grows or something forms, it's because there was already a cell there. Plate tectonic. So it's that idea that, all of the continents on Earth started out as, Pangea. So it was literally just one mass. And over time, because of the movement of the plates, we ended up with all these different continents that we have now. The laws of motion, and this is actually another in one of your other competencies, but you have to know all of Newton's laws. So with Newton's laws of motion, there's three laws. So the first one is an object at rest will remain at rest unless acted upon by an unbalanced force. And we'll take a look at that a little later. The second one is acceleration is produced when a mass is acted on by a force. And then the third one is for every action, there is an equal and opposite reaction. So it's important that you got to know those, you got to understand what those actually mean. And then universal gravity. So every object in the universe attracts every other object along the line of their centers. And there's a little bit more to it in terms of like by how much, that things attract each other, but just know in general that every object, you have gravity, I have gravity, Earth has gravity, but so does the moon, and, so does my dog, like everything does. And so everything's just always pulling at each other because of their masses. Okay, so competency 3 has to deal with how science impacts our daily lives, as well as influences, personal and societal decisions. So science isn't just something that's in the textbooks, and a lot of times that's what students think, right? Oh, I'm gonna go do science, but they don't understand that there's science all around them all the time. So you need to help your students make those connections. So it's not a matter of you telling them, oh, well, look, I did this and, or I saw this at home and this is science. It's about asking the kids for them to bring examples from their life so that you can help them make those connections. So those have to be, it's like their background knowledge that's being brought into the classroom. And so because of science, there have been a lot of advances in, in all sorts of things, right? But when it comes to that, there's always this, there's a line, right? And it's kind of like, okay, well, when do we cross it, and is it okay to cross it, and what are the implications for that, right? So there are things that maybe aren't being done. Maybe we have the technology to do them, but we don't do them due to ethical concerns or maybe personal concerns, or maybe even as a society, right? We just don't, we're like, no, like we're not okay with that, and so we're not going to cross that line. And other issues could just be economic, right? So maybe, there are places that they just don't have the resources to be able to use the technology, so it kind of limits them. But when it comes to the scientific principles, they should always be used to help you analyze those factors that influence personal choices, such as diet and exercise. So that's something that's very, very relevant to the kids, right? So it's not like, oh, I'm hungry, I'm going to go eat hot Cheetos for lunch. It's kind of like you have to help them understand, like, you're hungry, but, nutrients, like it's all connected, so we need to teach them about making those good choices for their physical health as well as their psychological health. And in terms of psychological, that, relates to drugs, it relates to tobacco, so just making those good choices and understanding that they have an impact on your body. Okay, so competency 4 has to do with understanding the unifying concepts and processes that are common to all sciences. So regardless of whether it's biology or physical science or, geological sciences, So science is just a process that helps us understand the world, and it's a way that we look at the world, but it's not just a thing we do in the classroom, right? So there's a little bit more to it. And so in science, there's going to be different disciplines. So in the elementary, right, there's there's life science, there's physical science, and there's earth science. But there's even more, I guess, like specific topics, I guess, within those areas. And again, it's just basically a method that all of them are going to use to collect and report data. So within any, science subject, whenever they're doing any sort of experiment, the variables always have to be controlled. So you may have like an independent variable or a dependent variable, and you got to make sure that your experiments are always done the same way to ensure that we're making a true experiment. So I can't just willy-nilly, oh, I'm going to test this out and whatever. I need to make sure that I know everything that is measured and everything that's having an effect on it. And so with science, especially in the lower grades, it's really important that we use models. And models are a good way for us to visualize these very abstract things. So, for example, here in the first picture, these are models that can be used to represent like atoms, molecules. These are things that are so small we can't even see them with a microscope, but using something like this, we can help students understand how they interact with each other. The next picture we have here is a picture of the skin. So it's a model of what your actual skin looks like. So, we can see it, but it's so small that we can't really see all the components that make it up. The next one we have here are edible cells. So when we talk about cells, again, you can see it through a microscope, but you really can't see all the little parts that make it up. And so when students make models, it's also going to help them understand that content. And the very last one, this is a model of DNA. So again, way smaller than even the components of a cell, but it really helps students to visualize like what that actually looks like, what the structure is, because it's one thing to tell them, it's another thing to make it concrete for the students. And so with the lower grades, we always need to make sure that we are starting concrete, like literally something that they can touch and feel, and then we can gradually move into those more abstract ideas. So when selecting activities, you always want to take into consideration the cognitive, social, and emotional development of your kids. So of course, in kindergarten, right, they are going to have specific needs versus like your sixth graders. So you can't just take, oh, hey, I saw this, cool activity in the fifth grade, I'm going to bring it down to the first grade. You're going to have to modify it for the needs of the students at that age. And so another thing that's out there are misconceptions, right? And so misconceptions are a problem in all of the sciences, regardless of age, regardless of type of science field. And for students, right, especially in the younger grades, they have this perspective of the world that's their own. Like they only see things through their eyes, and they still haven't quite been able to understand how to see things, in a global aspect, right? And so they're going to come to you with a lot of misconceptions. And once a student has a misconception, it's really hard to get rid of it, right? You can't just tell them, no, that's not right, because they'll be like, but that's what my mom said, or that's what, that's what my dad said. And so it's really about showing them. So again, it's having the students engage in those experiences and having them collect the evidence so that they can see, okay, yeah, I guess they were wrong, and then go home and, hey, mom, I did this experiment, and I saw that this happened. So with all the sciences, we want to make sure that they're able to really do it, so it's not just about seeing it, but it's really about doing it. And so again, as teachers, we need to make sure that we bring in the students' prior knowledge, and the best way is asking them, so trying to get them to give you examples of something, and so where they're coming from, and then you can help them to make the connections at that level. So again, it's always going to be direct, concrete activities, and then we'll gradually move to the more abstract. And that's even with your sixth graders. You want to start with something concrete, and then move to the more abstract. So This competency also talks about having to provide students the opportunity to work with students of different cultures and genders and ethnicities to broaden their experiences and their understandings. So, you know, again, they're only going to see things from their world, right? And their world is home, you know, and so that's all they're really exposed to. So when you bring them into the classroom, it's important that you're going to have students that have different, you know, cultures, or they've got different genders, different ethnicities, and so you want to have them provide them the opportunity to share some of that with the class and with their classmates, so that all of the students can learn a little bit more about the world in general. And so another thing it suggested in there was just kind of making sure that you have, you know, something which would be great is just posters, right? Things that are visible to also help students understand that science is not just for males. So science is a very male dominated world when it comes to scientists. So it's important that you help students understand that it can be anyone, you know, regardless of their gender, regardless of their ethnicity and culture. And then also for them to understand that there's a wide variety of science fields. So it's not just science, right? But there's like biology, and there's chemistry, and there's physics, and, you know, geology, astronomy, right? There's all sorts of different things out there. So if a kid says, I don't like science, well, you know, there's so many different sciences. There's got to be something you like, you know? So it's just kind of exposing them to those other things out there. And so the last one for this little unit here has to do with assessments. So again, with all of your competencies, you just have to understand how to provide appropriate assessments to monitor your students' learning. And you always want to make sure that we're monitoring regularly. So you're not just going to, you know, teach, right? And this goes for all of your content areas. We always have to monitor and assess them. So just like, you know, in class, when we teach, we stop and we have you write, or we stop and we have you talk, and then we have you share, and we're assessing you. That's ultimately, that's what we're doing. So we're assessing you to see if we're doing a good job of explaining. And so that's what you need to be doing with your students as well. So the purpose of our job is to get our students to learn, but how do we know if they're learning unless we check it? You know, we check for that understanding. So in science, you know, you'll have like your typical tests or quizzes that you would have in all your content areas, but some things that maybe in addition would be like a lab report. And so a lab report would just be a way to have students, you know, explain, you know, like what they saw in the experiment or in the phenomenon, and connect it to that content that you've talked about. They could also do presentations or projects, or, you know, create models. Those would be assessments that you would use that would be specific to science. And again, like I mentioned, right, in terms of assessing, it could be formal or informal. So like, you know, just kind of throwing a question out there for students to answer or talk about or write about would be informal. And then formal would be like, you know, a quiz or a test. Okay, you know, on Friday, we're going to take this, you know, assessment on your pod, or you're going to sit down and you're going to be, you know, everybody's going to be quiet. That would be more formal. Okay, so this is my informal assessment. So what I'd like for you to do in your notes is you're going to go ahead and write a summary of the content presented so far, okay? And then what we're going to do is read through it. So Sylvia joined us. Are you there, Sylvia? Hi, Sylvia. So I know you came in a little bit late, but if you can just go ahead and write a summary of the content that you observed so far, and then we'll have you all share it up.
Also, I wanted to tell you that we're going to be in a meeting with Mr. Aldaco at 1. So I just joined like to see what was going on.
Okay, no worries.
But at 1, so pretty soon I'll be you know, doing the other class, the other Zoom meeting.
Okay, not a problem. So this is being recorded. So I'll go ahead and I'll share the link with you all later.
Okay, thank you.
All right, so I'm going to give you 5 minutes. Okay, and so with that, we're going to go ahead and get on to our next competency. Oh, actually, before that, we have a little quiz. Okay, so we've got some sample questions based on these competencies that we just went over. And the Nearpod code is here, Sylvia, in case you didn't get it. Okay, so we're going to get into competency 7. And so again, with this one, when you're looking at your descriptors for competency 7, it's if you look at each of them, it's going to have you look up some like more information or more concepts. So I kind of covered the majority of them. And so with competency 7, this is dealing with forces in motion. And so what you need to make sure you understand is gravity, electricity, and magnetism. Okay, so those are the main forces based on this competency. And so when it comes to magnetism, it's just a force of attraction or repulsion between objects based on their charges. So there's ionic charges, and magnets are typically going to be metal, and they're going to have two opposite poles. So sometimes a magnet is like that U shape, but other times it's literally just a bar. And so one side's positive and one side is negative. And we know that opposites attract, right? So positive is going to go in negative, but if I put two positives, they're going to repel. If I put two negatives, they're going to repel each other. And so when we think of a magnet, we want to understand that there's actually an area around it that's like attracting, that's giving off that attractive or repulsive fields. So that's called the magnetic field. And Earth is like a giant magnet, okay? And so gravity is what that magnetic field is. So that's why we literally have a North Pole, we've got a South Pole. That's why a compass works, right? Because it's literally being pulled in that direction. And so all objects on Earth, including the atmosphere, right, which is the air and everything that's in there, they wouldn't be held onto the surface without it. So gravity is what keeps all those things in place. And so we kind of talked about gravity and how everything has gravity, right, regardless of what the object is or the size of the object. But we do know that the more dense an object is, the stronger its gravitational pull. So, when we think about the planets, right, there's planets of all sorts of different sizes, and the more massive planets are going to have much stronger gravity. And the smaller or less dense bodies out there are going to have less gravity. So that's why when people go to the moon, right, it's smaller than Earth. And so the gravity is different there, right? So you've seen astronauts, they jump and it's kind of like this like slow motion, and it's because there's not as much force that's pulling them down. Okay, so then the next thing we have is position and displacement with distance. Okay, so position in general, that term just means where something is located. And for distance, that's how far an object has traveled. So here I've got an example. So I could have a starting point, which is over here. And I may walk, I don't know, take the long path, and I'm going to travel a certain distance. And that's literally like the path that I have traveled. I could measure that out. But if I look at how far I got from my original position, that would be considered my displacement. So maybe I traveled, I don't know, 100 meters, right, to go all around. But when I look at point A to point B, maybe the distance only like 50. So I got to understand the difference between those two terms. And in science, they use these other terms, which is scalar and vector. And so a scalar has to do with any number that doesn't have a direction. So, if I'm talking about distance, this didn't have anything with, where I was going, north, south, east, or west. It just was just measuring that distance. But when we talk about displacement, that has to do with where I moved in relation to my starting point. And so displacement has to do with position. And so it is a vector quantity. So we're going to talk about, you know, different types of measurements in this competency. And some of them are scalars and some of them are vectors. And that's what makes them different. Okay, and so what I did in, so this Nearpod is a I'm gonna give you the code for the self-paced Nearpod. So what you can do later is you can come back and then I put little mini video clips in there so that you can play them and it gives you some more information. Because obviously there's a lot of content, right? So I'm not gonna be able to cover everything. Okay, so the next one is motion and speed. And so, you know, you hear the term speed, you hear the term velocity, and again, in the real world, right, we think of them as the same thing, but in the science world, one of them has to do with direction and one of them doesn't. So one of them is a scalar and one of them is a vector. So speed is just the distance traveled over time. And because it has nothing to do with direction, it's a scalar quantity. So, you know, my speed on the freeway is, you know, 50 miles per hour. But when we talk about velocity, that has to do with direction as well. So my velocity could be 50 miles per hour headed north, or, you know, 50 miles per hour headed to Ulta, right? So that has to do with direction. And so when it comes to calculating speed or velocity, you would use the formula that's right here. So average speed is equal to total distance divided by time. And when it comes to motion and, you know, dealing with speed and acceleration and, you know, displacement, there are graphs. Students will have to know how to graph things. So you just have to, in general, you know that you've got your x-axis, you've got your y-axis, and the axes always have to be labeled. So if I'm talking about time, you know, time is down here on the bottom, then that means my time is increasing as I go this way, right? For velocity, you know, my velocity is increasing going this way. And so because velocity is a vector, you could have positive or negative velocities, you know, depending on where that direction is taking you. Oops, what happened? Okay, yeah, so that was a video. All right, so here we've got some matching just with some definitions. Okay. So the next thing we have here is Newton's laws. Okay, so Newton's laws of motion, again, like I mentioned, you know, they mentioned them at the very beginning. It has to do with one of those other competencies, but then this is also one of the competencies in terms of content that you have to understand and be able to teach your students. There's 3 of Newton's laws. And so the very first law is the law of inertia, which basically says that an object at rest will remain at rest unless an unbalanced force acts upon it. And so with this one, the example that they always use is being in a car, right? Or being in a car accident. And so when you're moving, you know, your body's moving at 30 miles per hour. Well, if you slam into a pole, your body is going to keep moving at 30 miles per hour. And that's how people get ejected from their vehicles. And so same thing goes if you're stopped at a stoplight and someone comes from behind you and they hit you, you know, you're going to be jolted back because your body's at rest and it wants to stay at rest. So when something tries to move you, you're going to end up, you know, being jerked in another direction. And so you feel that when you're, you know, in the car, you know, when you're turning, you know, if you're turning to the left, your body moves to the right. If you're turning to the right, your body moves to the left. You know, and other examples would be if you've seen that trick where they have like a table and they've got, you know, plates and dishes on it and there's a tablecloth underneath it. And then they rip the tablecloth out and all of the dishes stay. That's the law of inertia. So the objects are on there, they're at rest. And so if you pull that tablecloth out fast enough, there's nothing acting on them. So they're just going to stay there. They're not going to move. And so again, this relates to a whole bunch of different things. You know, it has to do with, you know, out there in space, you know, so that when astronauts get out there, they actually end up in Earth's gravity, Earth's gravitational pull. So they're not even, they're not really moving. And it's just a constant state of falling, I guess it is, which is why they're kind of floating around there, you know. So it's, again, Newton's law is right, it relates to that. So again, this is something that has been tested, you know, out in space. If you push something, you know, it's just going to keep going at that same, you know, velocity or speed, unless something else acts on it. So, and here on Earth, we have the atmosphere, and that's why, you know, if I'm, you know, riding my bike, eventually I'm going to stop if I'm not pedaling, because there's friction, there's air resistance, you know, there's forces that are acting on us. Okay, the second law of motion has to do with acceleration, force, and mass. And so the formula can be written different ways. In the high school, we usually teach the students force is equal to mass times acceleration, because they do a lot of calculations with it. But in the elementary grades, it might be easier to represent it this way. So acceleration is equal to force divided by mass. And so in other words, in order for an object to change its velocity, a force has to act on it. And the mass of that force is what's going to have an effect on it, right? So if I'm trying to push, you know, this giant elephant, right? I'm little, you know, like I'm not going to be able to do much, you know, even if the elephant's on skates, right? Because I don't have a lot of mass, I'm not going to be able to cause that elephant to accelerate very much. Okay, and so, you know, the same thing goes if I have a, you know, if I have a ball and I'm throwing a bowling ball, you know, versus throwing a baseball, because of those different masses, even though I'm exerting the same amount of force, they're going to have different amounts of acceleration. And so that's how those are related. You have to know what the term force is. So force is just a push or pull on an object. And again, force, because it's related to this law, but it's also related to other aspects of this competency. Okay, Newton's third law is for every action, there is an equal and opposite reaction. So every force going in one direction, there's going to be a force that's pushing on it in that opposite direction. So the examples here, you know, if you've ever gone swimming, right, what do swimmers do? They push off the wall. And so they're pushing off the wall to go in one direction, but the wall is actually pushing back on them. If the wall wasn't pushing on them, you know, when they would push out, they'd go straight through the wall, right? So since they don't, there's a force that's actually pushing back on them. Another example we have here is the balloon. So if I let a balloon go, you have the force of the air, you know, pushing in one direction, but then you're going to have so there's, how should I say? So there's the air moving out of it, but it's pushing the balloon in the opposite direction. So just equal and opposite. Other examples I've seen in textbooks are like you have two people on roller skates, you know, so you have two people on skates, and if they push each other, they're going to just move in opposite directions. When you're in a boat and you're rowing with the oars, you push one way, but the boat goes in the opposite direction. Okay, and so for that one, again, there's a video that's going to be related to Newton's laws. So then the next one has to do with machines. So a machine is just anything that makes it easier to do work. And work has to do with the movement of an object, basically. So applying a force, but that also causes the object to move. So an example of, you know, not doing work would be like if I'm pushing against the wall. So if I'm pushing against the wall with all my might, you know, I could be exerting a ton of force, but if the wall doesn't move, then I didn't do any work. Okay, so that's kind of what the science definition of work is. So you have to exert a force, but that force has to make the object move. And so when we think of moving things, right, or doing work, there's ways to make that work a little bit easier. And so a simple machine is just a tool that's going to help us do that. So for example, if I'm looking at this guy here who's pushing the box, the guy could actually just lift it up there, right? So the box could be on the floor at the base of the truck, and he could lift the box up there, but it would be really, really hard for him to do it if it's heavy. But when I do it, put an inclined plane there, then he's able to push it up with less force. And so in terms of the amount of work, if we were starting from the bottom to the top, the amount of work may be, and sometimes it may be the same that they're doing, because it's moving the same distance, but maybe the work could be less. Maybe he needs to do less, he's going to use less force to do it. And so there's a video for this one as well that kind of talks about how those are all related. But some of these simple machines are going to make the work easier. Some of them, especially pulleys will change the amount of work, by a certain fraction, depending on how many pulleys you use. And so a complex machine is basically just two or more simple machines that are put together. Again, with these simple machines, all they're really doing is changing the direction of that force, which is making things easier. Okay. All right, so that was competency 7. So the next competency we have has to do with physical and chemical properties. This is kind of like the chemistry part, right? So matter, we got to understand what all these definitions are. So matter is anything that has mass and takes up space. And then mass is just a measurement of that matter. So mass is an amount that will stay constant. So how we talk about like weighing ourselves, right? So, oh, I'm gonna weigh myself today, oh my gosh, I weigh 200 pounds, right? Like that's not great. Well, maybe I'll just move to the moon and up there maybe I'll weigh 100, right? So depending on gravity, that's gonna have an effect on your weight. But if I were to measure my mass would be the same regardless of whether I'm here or I'm on the moon. Mass always stays the same because I'm made up of the same amount of matter. And then volume has to do with the amount of space that matter takes up. So examples that we have here have to do with our solids, liquids, and gases, right? So if we're talking about these containers, right, for the gas, the volume of the gas is going to be the volume of the container. It's going to take up all of that space. But the volume for this liquid, it's taking up less space. So the volume is going to be different in comparison to the gas. And if I look at the solid, it's still taking up less space. Maybe I have the same amount of matter and maybe they all have the same amount of mass, but in terms of the space they take up, which is volume, those would be different. And so whenever you hear the term density, density is taking into consideration the mass and it's taking into consideration volume. Okay, so in the chemistry component, there are also elements, right? So matter is made up of elements, compounds, mixtures, but an element is going to be found on the periodic table and it's made up of only one type of atom. And the periodic table, this one isn't complete, it's just an example, but on the periodic table, those are the only elements that we have. So you can't, some of them, they have been synthesized in the lab, but you can't just go and like find a new one, like this is it, these are the ones. And these are like the most basic, I guess if you're break down in all matter, this is like the most basic component that everything in the universe is made out of, okay? And so an atom, whenever we talk about atoms, those are going to be the smallest component, right? With, my elements are going to be made up of atoms, but it's like the smallest component. And these are made up of protons, neutrons, and electrons. And when I put two or more atoms together and I bond them covalently, then they form molecules. But two or more different elements bonded ionically is going to be a compound. And so it doesn't sound like you have to know like too much more about that, but you got to make sure you understand those general terms. Okay, so when we get to properties, a physical property is just a way to describe matter. And so, students even in the, in kindergarten, they can come up with physical properties because it's something that they're able to observe, like, with your eyes, with your hands, you can feel it. So for the most part, a physical property could be how something looks and feels, but it could also be something that may have already been like measured, like the the boiling point is a physical property. So we know that water boils at 100 degrees Celsius. So that's not something that I can just like see, it's something that we kind of already know about it. So some examples would be hardness. Luster has to do with how shiny something is. The color of something, conductivity, whether you can put an electric current through it. And then a chemical property is a way to describe how matter reacts with other matter. So for this one, there's really, like, I guess some things we already know, like we automatically know that they're going to react with something, but for other things we don't know. It's kind of like, well, let's test it out. Let's see if it's going to react to this flame. Let's see if it's going to react to this oxygen. Let's see if it's going to react to this acid. And that would be a chemical property of a substance. And so with these properties, these are basically just ways to describe matter. So it could be anything, it could be a way to describe your pencil or your paper or a ball, my Kool-Aid, right? It's just a way to describe them. Okay, so then the next one is physical and chemical changes. And so these concepts, they're taught all the way up into high school. And I'll tell you that even in high school, students get confused on the differences, right? Because we see physical and chemical, but students don't understand the difference between a property and a change. So you have to understand the difference. So with a physical change, it's literally changing the substance, right? So with the other ones with properties, I'm just describing them. But with a change, I'm changing them somehow. And so a physical change changes the object somehow, but it doesn't change its composition. So like, for example, I had paper, right? I had full sheets of paper and I folded them. I cut them, but it's still just paper, right? Like I didn't change what the composition of this was. So that's an example of a physical change. So examples would be, cutting paper, melting ice, mixing coffee and water. It's still just coffee and water. Like there's nothing about those, about the matter that has changed. But a chemical change would be when I change something and it reacts with something else to become a new substance. So what I've heard sometimes, which is not the best way of teaching it, but in the lower grades, they like to tell students, if you can change it back, it's a physical change. So like if I have an ice cube and it melts, I can just freeze it again and it's back into an ice cube, right? It's still, so that's kind of how they talk about a physical change. But the problem with that is like, if I cut my paper, I can't like, you know what I mean? Like I can't put it back together. If I crack an egg and the egg breaks, I can't put that egg back together. And so that's a misconception that you don't want to have or use with your students, because then kids think, oh, but if I can't put the egg back together, then it's got to be a chemical change. But that's not the case. It's still just an egg. It's just a broken egg. So with a chemical change, the way to remember whether something is a chemical change is to pay attention to these indicators. So, if I take my paper and I set it on fire, my paper is going to change color. It's going to turn black, right? It's going to smell different. It's going to, when I light it on fire, it's going to give off light and heat. And all of those are indicators of a chemical change. So if I crack my egg open, it still smells like an egg, didn't change in color, I didn't get a gas out of there, it didn't get hotter or colder. So I know that it didn't meet these criteria of a chemical change. So when I would teach this in chemistry, that was kind of our litmus test, to determine whether it was chemical or physical, because my students would come to me with that misconception of, you can change it back, if you can change it back, it's physical, but that's not always the case. And I know you joined us a little bit late, Deanna, but I put on the Nearpod, I put videos in there so that you can take a look at them later. Okay. Okay. And then there's a Nearpod code if you don't have it already.
I'm sorry, could I have it again real quick?
Okay, so then the next one we have is competency 9, and this one has to do with energy and interactions. And so the teacher understands that energy and interactions between matter and energy, there's a whole bunch of different ways to look at this, and there's a whole bunch of different types of energy. So again, I'm just going to kind of briefly go through it. But the one thing you have to know is the law of conservation of energy. And there's actually, I think it's competency 10, also refers to the law of conservation of energy. So that just means that energy is conserved, and that means that energy cannot be created or destroyed. So again, right, misconceptions that students may come to you with, they may think that, I don't know, like they'll tell you, Miss, I'm all out of energy, right? Like I gotta go rest, like I'm all done. But it's not that they literally ran out, it's that their energy was transferred into something else, right? So maybe they're really hot, maybe they're all sweaty, those are transfers of energy. And so there's a whole bunch of different forms of energy, but we got to understand that the energy can just be transferred. So like if I think of, lighting up a light bulb, there's electricity that, maybe came from a turbine somewhere, that maybe came from like wind energy. And so, that wind energy got turned into that mechanical energy, got turned into electrical energy, transferred to my light bulb, which gave me light energy and heat energy, and that's just that cycle of energy just being transferred from one thing to another. Okay, so it never ends. It's just always in this cycle. And so the two main types of energy that you need to know are going to be kinetic energy and potential energy. And so kinetic energy is just the energy in motion or energy of motion, and potential energy is stored energy. So sometimes they just, I guess I hear them mention like those two things, but there's like different types of potential energy. So potential energy could be, like me holding, I've got a flashlight here, like the fact that I'm holding it here, it has the potential to fall, right? But my flashlight here as well, it's got a battery in it, and that battery is chemical potential energy. So it's stored energy that I can click on my flashlight, and then that's when I'm going to use the energy. So I could eat my food, right? At lunchtime, I ate food, and that is chemical potential energy as well. So I'm eating it, and that's going to go into my body. It's stored. And once in my body is going to break it down and turn it into the energy that I need to actually function. So there's different types of potential energy. For kinetic, it's really just movement. Anything that's moving is going to have kinetic energy. And that goes down to your molecules, so like when we're thinking about a gas, the atoms of gas moving, that's kinetic energy. So energy is also related to heat. And so we hear the terms temperature and we hear the terms heat, and we think that they're, similar, or they're the same thing sometimes. But temperature is just a measure of the kinetic energy of an object. So, if I have water and I measure the temperature of it, and it's like, I don't know, 80 degrees Celsius, right? So it's kind of warm. If I heat it up, and it gets to boiling, it goes to 100 degrees Celsius. Well, that just means that the water molecules are moving faster, and that's why it's picking up that temperature. So if you think about it, right, when we go down to freezing, if I take my ice cube and I freeze it, it's going to be 0 degrees Celsius, and that's because the molecules they're not moving very much. So you can't, for like ice, you can't go any lower than 0. It's just going to be at 0. Like that's it. They're not moving anymore. But for other substances, they can go lower than that temperature. But once they hit that solid, those molecules they're not moving. So heat is going to be the total energy of atoms or molecules. So they're kind of related, but they're not the same thing. And so the other thing we have to understand about energy is that the sun is just the source of all energy on the planet. So the sun is generating this energy, which is radiant energy, right? It's giving off that light. It's producing heat energy, and plants are the first ones to pick it up. So the plants are going to pick up that energy. They're absorbing that energy, and then that's how they're going to make their glucose or their food. And then that's how they power themselves. And then all living organisms are eating something that either ate a plant, right? Or they're eating the actual plants, and that's how they get their energy. So us, maybe I'm not a vegetarian. Maybe I don't like vegetables, but maybe I love my beef, right? Well, my cows are eating plants. And so like we're all connected back to that sun. Okay, so it's just this big cycle, but everything is coming from that sun in terms of that energy. And so photosynthesis is that process by which plants capture that radiant energy and then they turn it into that chemical potential energy, which they use for their food to help them function. Okay, so the heat transfer has to do with these three main, three main types of heat transfer. So you want to make sure that you understand what these three things are. So conduction is just the transfer of heat through a solid. And so the example that they have here, right, they have a metal rod and they're holding it into the flame and you have to use gloves, right? I'm sure this has happened to you. Maybe you've had a metal spoon and you're heating something up. You walk away, you come back, you touch the spoon and I burned myself, right? So that's conduction. It's just transferring those molecules and again, heat has to do with those molecules moving. So the molecules are moving really, really fast, like at the heat source, and they're making the molecules in the metal rod move. And that's why it kind of like works its way up until, all the molecules are moving at that same speed. So that's why, for example, if there's a fire in your house, they tell you to touch the door first, right? So you're going to touch the door, and if the door feels hot because of conduction, right, you know that the fire's on the other side. So, don't open that door. So then the other type of transfer would be convection, and this one has to do with a transfer of heat through a fluid. And this again, coming from teaching in the high school, this is confusing to understand because when we think of a fluid, we think of a liquid, right? But a fluid is a liquid or a gas. And so convection can happen through the air, right? So right now, I'm sure you all have maybe the heater on in your house. And so you can, raise your hand up to the ceiling and you should be able to feel warmer air, up on the top. And so there are currents of air that are moving through your house and the heat is being transferred by convection. Okay, so it's not a liquid, right? But it is considered a fluid because it's a gas. So another example of convection would be like boiling water. So if you have your pot, you're watching the water boil, you start seeing those bubbles and they kind of like are moving in this like circular motion, right? As they go through, that's convection. And so the same thing with your heater in your house, you have that heat being pumped out and it's moving in a current. When your heater turns on, you can feel that like wave of heat coming out. You can feel that cold, wave coming in when they open the front door or something. And so the last one is radiation, and this is just the transfer of energy through an empty space. So for example, we get our heat from the sun, through radiation. The sun's not touching the planet, right? The sun isn't, there's no fluid in space. It's an empty space, right? There's nothing out there. So the radiation is how that heat is being transferred to us. And so in this example here, you may have currents, right? If you've ever had a flame, you're going to see those little things kind of popping off because literally that heat is causing this, like the air to be heated. And so you feel that heat coming up as like a fluid. But then if you're next to it, you can still feel the heat coming off as radiation. So it's not the hot air that's being warmed, but it's just like heat in general. Questions on this term? No? Okay. And so again, these ones can be a little bit confusing. So there's, again, there's a little video in here that you can watch. So phase changes are something that you need to understand as well. And so a phase change, you all know what they are, but maybe not the way they're described here, right? So you know that when we have something melting, right, or something boiling or something, going straight into a gas, those are all phase changes. So melting is just the point at which a solid turns into a liquid. Boiling is when a liquid turns into a gas. And then evaporation happens when a liquid goes straight into a gas, but it doesn't have to do with heating, right? It doesn't have anything to do with that temperature. So you could just leave if you have a cup of water, you could just leave it out, and over time that water is going to turn into a gas, and that's just evaporation. Condensation is the opposite. So you have a gas turning into a liquid, and you'll typically see that, like, on a hot summer day, you've got a glass of lemonade, and all of a sudden you start to get this water that forms on the outside. That's condensation. So there's literally water in the air, and it's turning into a liquid when it's touching that cold glass. And so looking at this graph here, when we think of phase changes, and this is a misconception that some people have. So students, right, if they're like, okay, my water's boiling, I want to make it even hotter, I'm going to raise the temperature even higher. Well, when something reaches its boiling point, it actually stays the exact same temperature, and it won't change. It's never going to change as long as you have both phases of matter being present. So as long as I have a gas and I have a liquid at the same time, the temperature is going to stay exactly the same. And the same thing goes for freezing. So if I have an ice cube, water freezes at 0 degrees Celsius. If I put it into I don't know, some industrial freezer that's, negative 100 degrees Celsius, when I take out my ice cube and I measure the temperature, it may be lower than that. But if I start letting it melt, it's not going to melt until it reaches 0 degrees Celsius, because that's its melting point. Okay. And so once I have ice and water, it's going to be the same exact temperature until all the ice is gone. Then that's when the temperature can actually start to rise. Okay. And so again, just misconceptions that people have, your kids, if I've got my water boiling, I'm gonna make it hotter. I'm just gonna heat up turn up the flame, but it's not gonna have any effect on it. Okay.
Are all examples of heat transfer. In simple terms, heat is the transfer of energy from objects of different temperatures. As objects warm up or cool down, their kinetic energy changes. Kinetic energy is the energy of motion. Temperature is a measure of the average kinetic energy of the particles in an object. As temperature increases, the energy of motion increases. As the water warms up and the temperature increases, you can see an increase in the movement. Heat can be transferred in at least 3 ways: conduction, convection, and radiation. Conduction is a process in which the transfer of heat takes place between objects by direct contact. It is most often associated with solids. The key to conduction is direct contact. The heat of the pan is transferred to the mini pizzas. The energy of the frying pan is transferred to the eggs. Notice that they are in direct contact. Convection is heat transferred by the movement of a fluid such as air or water when the heated fluid is caused to move away from the source of heat, carrying the energy with it. It occurs due to density. Lava lamps are examples of convection. As the liquid is heated, it rises and falls as it heats and cools. As the paper burns, the air is heated up and begins to rise. The burning paper is swept up in the convection current, cools, and falls back down. These beans are another example of convection. As the beans warm up, they rise and then cool and fall back down, and repeat this over and over again. Radiation heat is transmitted without any physical contact between objects. Watch how the temperature of the lamp is transferred to the thermometer without touching it. These alligators and lizards use radiation from the sun to warm their bodies. If you'd like to know more about heat transfer and conduction, convection, and radiation, this playlist will help. And as always, thanks for watching, and Moo Moo Math uploads a new math.
Okay. All right, so next thing we have is electricity. And so electricity is related to that energy, okay? So electricity is just electrons moving from one atom to another. And electricity has to start with an energy source. So I can't just like, get a light bulb and put some wires together and the light bulb's gonna light up. So there has to be some sort of energy source that's gonna provide that electricity to move. That's gonna provide the electricity. And then in order for electricity to move, there has to be a conductor, right? So there has to be current, which is that flow of electricity, but it has to move along a conductor. And metals are really good conductors. So that's why like all of our wires, for anything that's going to be plugged into an outlet is going to be made out of a metal. Even just like looking at my flashlight here, there's a metal, coil in there that's going to help to conduct that electric current from my battery. And so an insulator is going to be something that stops the flow of electricity. So again, right, talking about our pans, if we're cooking and the handle is really hot, you're going to get a pot holder, right? And the pot holder, maybe it's made out of silicone. So silicone is an insulator. It's not going to allow electricity to transfer through it. Maybe it's made out of like a thick fabric, right? That's like cloth. It's not going to allow electricity to transfer through it. And so if you see, the people working on like the electric poles, they're not up there working with their bare hands because our skin is actually a conductor, so we're going to be able to, you can touch something and you're going to get shocked. I don't know if any of you did this as a kid, but you got like a 9-volt battery, right? And you touched like maybe the end of it to like your tongue and you got zapped, or, you touched the 9-volt battery, you touched one part and you held your friend's hand and then they touched the 9-volt battery and you all made a circuit, right? So it has to be a circle and the electricity transferred through, and you can literally feel that jolt of that electricity going through your muscles, okay? So that's a circuit. So an electric circuit has to be a circle, okay? So there has to be the energy source or wherever that electricity is coming from, and then it's got to travel away and back to that energy source. If it doesn't, like in this case here, this is a switch. If the switch is open, there's no circle. And so the circuit isn't complete. So that battery is never going to turn on. Okay. And so that's why we have switches, right? Our switches in our house are what's stopping that that circuit from making that circle. Okay. And so even thinking of like our electricity, right? I know that could be a misconception too. If I'm like, okay, well, my cell phone, I'm plugging it into the wall. It's like, how is that a circle? Well, the current that we have, so it's like alternating current. So it's like sending it in different directions, but there's actually like 2 wires going in. And so we've got like those 2 prongs. So it's actually making a circuit. It's making a circle. Okay. And so again, this goes with anything that has electricity. So it could just be a battery. It could be, an outlet in the wall. It could be like a generator, that you have. But all of those, it has to make a circle to allow that electricity to move along that and allow that current to move along that circuit. Now, sometimes you can make a magnet using electricity. So you could, take electricity, a wire, and wrap it around something. And if you have like multiple, I guess, circles or like wrapped around it, that electric current will actually cause a magnet to form. And that's called an electromagnet. Okay. All right. So the next part here is light energy. And so with light energy, we've got to understand that light travels in waves. And that there is this electromagnetic spectrum, right? There's this whole huge variety of different waves out there, but light energy, or like what we can actually see with our eyes, is actually only a really small component of that spectrum, of that electromagnetic spectrum, okay? So within that electromagnetic spectrum, or all these waves that are out there, there are things that we use, right? So you all have probably had an X-ray, you know, maybe you've got a remote control, right, for your TV or something. Your cell phone is going to have waves that allow it to work. We've all got Wi-Fi, a radio, and even your microwave. All of those are waves, and it just has to do with their frequency. But what we can see, the only waves that we can't see are going to be within this small spectrum here. Okay, so it's just a small portion that we can see. Now, some animals, like such as insects, they may be able to see a little bit and a little bit different portion of that spectrum. So that's why they may see like through UV. Okay, so like they won't see colors the way we do because they're looking at it. They're seeing that ultraviolet spectrum. Now, when we think of light energy, we also want to understand that, or should I say, when I think of just light, right? If I think of like the light coming out of the sun or the light coming out of my lamp or a flashlight, we see it as like clear or maybe like a white color, right? But it's really actually made up of the rainbow, okay? And so the way that I'll be able to see that rainbow is by refraction, so bending of the light. So if we bend the light, and you may have seen it with a prism, right? So I have like a prism, like the triangle, like Pink Floyd, right? Pink Floyd album, you know, so you have the light going through, and with that prism, it's going to bend it, and then you're going to be able to see that rainbow of colors. So our light is actually made up of all the colors, okay? And so when I actually see color, like if I'm seeing the color pink here, it's because the color pink is being reflected back, and that's why I see it. So the light itself is showing all the colors on here, but the only color reflecting back is pink and blue. Okay, so that's how we're able to see colors. And so when we think of a rainbow, like, you know, after it's rained, right, I'm only going to see a rainbow if there's moisture in the air. And so that means that there's water droplets in the air, and the water droplets are acting as a prism, and they're bending the light that's coming from the sun, and we're able to see this rainbow effect. Okay, so it's just that bending of light. Now, refraction can also happen in just plain water. So we'll see a little video right now, but I'm sure you all have been in a swimming pool, right? Maybe you've got your feet in the water and your feet look blurry, or your feet look like maybe they're further ahead of you or they're further behind you. And that's refraction. So as the waves of light come into the water, because the water is more dense, it slows it down. So just like if you were running, right, and then you try to run in a pool, you run a lot slower, right, because there's that more resistance. So that's the same thing that happens with light. The light's moving fast, but once it hits the water, it bends because it slows down. And again, just refraction. Reflection is just light bouncing back. So, you know, we all have a mirror at home, and so we're able to see ourselves because literally the light is going, you know, into the mirror, hitting the back of the mirror and bouncing back into our eyes, and that's why we're able to see ourselves. So, and all of this is because they're all waves. Okay, so waves, it's like a particle, and that particle can move in different directions, right? It can move at different speeds, and that's why we see all those changes. So our example of refraction in everyday lives, right? So again, just like looking at water, seeing things in the water, you can see how that light is actually bending it so that the object looks different. But refraction can be used for our glasses or our contact lenses or a microscope or a telescope. And all it is you take a lens and you bend it a certain way, and you can actually cause the light to bend the way you want it to bend, and you can have it focus in a different area. So the reason that our glasses work, so I wear contacts, I'm like super blind. So I wear contacts, and so for me, right, I'm super nearsighted. Like literally when I wake up in the morning, if I want to see the time, my husband always laughed when we first got married, because I used to wear a watch. I had to go to bed with a watch. You know, this is before we had the cell phones we have now. So I would get up in the morning and I would put the watch to my face like this, because literally that's how blind I am. Okay. So for me, I have my contacts a really strong prescription. And what they do is they just make sure that they focus the light on the back of my eye, so that I'm able to see it in focus. Okay. But if I don't have it on, my eyes are so bad, right, that it focuses it in the wrong area. And that's why I see things blurry. So same thing with like, things in outer space, things are super, super far away, but they're able to use these use these lenses to bend the light so that it's like the objects are right there, they're on the screen right in front of you. But it's all about that focal point and how far close it is that we want it.
That did not work out the way I thought it would, Robo. Let's try that again. Was that you?
Sorry, Reem. I'm afraid of the dark.
The storm must have knocked out all the electricity. Robo, where's the fuse box?
It's in the back, near that table.
Grab me a flashlight, will you? What's wrong?
I can't find the flashlight, Reem. I'm so scared.
Don't be scared. We can just use a laser light.
Yeah, sure. What's the difference between a flashlight and a laser light?
It looks like the laser's only one color.
What do you mean one color? Isn't a flashlight one color?
Well, light travels in waves, and a flashlight is usually white light. But white light is actually a combination of all different light waves.
That must mean the laser emits only one wavelength of light.
Right, it's light of the same wavelengths.
So if it's only one wavelength, that must mean the light is weaker. So I bet we can't use it.
No, it's not weaker. It's beams of light, with all the same wavelengths traveling in unison. It's called cohesion. It results in a really strong beam.
On the other hand, the light from a flashlight is weaker because the light spreads out as it travels away from its source, the bulb.
Well, as long as it emits light, we should be able to use it.
Check. It definitely emits light. Great, but it's stuck. I'm not sure why.
Can you fix it?
I can't do it.
Look at that! The light has bent slightly through the gel. This must be refraction.
What's Chin?
It happens when light passes from one transparent material to another transparent material of a different density. Do you get it?
Yeah, not in the least.
The light is entering at one angle and leaving at another. It's bending. Bend it in your direction.
Genius. But how?
Try other objects in the lab. That's it, Robo. Keep curving it around this way.
I bet this black book will help bend the light in your direction.
Try everything we got.
Nothing.
Wait.
What?
Go back to where you were.
With the book? But it didn't work.
No, with your body. Good. Move a little to the left.
Good call, Reem.
Now move a little bit more to the left. Perfect. I orchestrated a pretty sweet solution.
I was going to say that I carried out an amazing solution.
Now what were you saying about reflection and refraction?
It looks like we experienced all of the ways that light travels through space. Reflection, refraction, and absorption.
You mean all the ways that light doesn't travel through space? We were in the dark.
No, I mean the laser light. When light bent through the clear gel and glass, that was refraction.
And then, when it bounced off of your opaque, smooth metal body, it was reflection. And the book didn't work because rough surfaces reflect light in all different directions. Also, dark surfaces absorb more light energy than light-colored ones. Since the book was black, not much light was left to reflect. Got it. How's the laser light stuck anyway? Is this your doing, Robo?
Oh, yes. I did that last week because I needed the laser to stay in place while I worked on something.
You're lucky that reflection and refraction saved the day.
Okay, so that's light. So the very last one is sound energy. And so sound is going to travel in waves as well. Okay, so sound and light are both traveling in waves, but sound is going to move through different mediums, such as solids, liquids, and gases. So sounds are going to travel best through solids because the atoms are more compact. So I know that was a misconception as well. I think I even had it, that I thought the sound was going to travel best through a gas, right? But it actually, because it is a wave, if you have a solid, it's actually like the molecules are just a lot closer together, so the wave is able to travel through it faster. Whereas in the air, the molecules are much farther apart, so it takes longer for those waves to travel through. So that's why, for example, maybe we've heard something in space, right? Well, it was traveling for who knows how long, because there's like hardly any particles out there, right? So it takes a really, really long time for that sound to get to us. So there are two different types of sound waves. So there's longitudinal, which move parallel to the direction of the wave. And then there are transverse, which move perpendicular. But again, sound is just another wave. Okay, so we're going to go ahead and summarize. Let me see if did we see all the videos in this one? Okay, yes. So we're going to go ahead and do a protocol, which is called Essence. And so what you're going to do is, there we go. So you're going to go ahead and you, Trina and Deanna together, you're going to try to come up with a 32-word summary to summarize this one competency dealing with energy. Okay, so a 32-word summary. Okay, so the last competency we're going to take a look at is competency 10. And so this, again, just ties back with energy transformations and conservation. So with this competency, this one's talking a little bit more of how energy is going to be transformed into a different type of energy. So I mentioned that earlier, right? So we know that there's the law of conservation of energy. Energy can't be created or destroyed, it's conserved. So it just means that it's going to change from one thing to another. Another thing that this one's also going to talk about, it deals with the types of, or should I say, with the sources of energy that we have. So, there's non-renewable resources that we use. So, we all have natural gas at home. People use coal and, there's oil. So those are non-renewable, right? Whatever's out there is all we have. But then there's also going to be renewable resources. So there's wind energy, there's solar energy. And again, they're all, producing energy. That energy is all going to be transferred, but one, is going to run out at some point and the other one is going to always be there. So again, just remember that it's always going to be transformed from one form to another. So the energy never just runs out. It's just going to turn into something else. So something I would suggest for this one, for this competency, is kind of looking up those different types of energy that you could have. So, I mentioned there's like solar energy, there's radiant energy, there's light energy, sound energy, heat energy. There's just a whole bunch of different things out there: mechanical, potential, kinetic, right? And all of them can be turned from one thing into another. So an example that we have here, right, and I mentioned this one earlier, is just that the sun gives off radiant energy. Plants convert that radiant into chemical energy. Animals eat the plants and turn it into chemical potential energy, which helps the animals move, and that's kinetic energy. So it's just this, never-ending cycle of transfer.
I have a question on this one.
Mm-hmm.
So when we discuss renewable versus non-renewable resources in school, non-renewable resources are described as items that are, like, once they're used, they're gone forever, they're destroyed. So does this have to do with energy, or does it have to do with like the item itself, if that makes sense?
Yes, good question. So it has to do with the actual item itself. So, we've got gas, or not gas, we've got coal out there, right? There's coal like in the mountains, but once we use up all the coal, there's no more coal that's going to be there, right? So it's something that's eventually going to run out. It doesn't mean the energy's gone, right? I can burn that thing to get energy out of it, but that energy itself is just going to be turned into something else, right? So when I burn up the coal, I'm going to get light energy, I'm going to get heat energy, you know, maybe even sound energy, right? If you hear like the popping of it as it's burning, so that energy will still be out there, but the coal itself is eventually just going to disappear. So yes, but good question there. Okay, so we're going to go back, and since we've still got time, we're going to go ahead and watch these little video clips so we can kind of review these little topics, and then we'll go ahead and wrap it up with a time to climb. So again, you'll go ahead and be able to practice answering some questions.
I always have trouble with the time to climb because I always misclick, or it just pauses and then it'll click something else. So just letting you know before you think I don't remember anything.
That's okay. All right. And for Anna, who just came in, the code's up here on the top, okay? Oops, wait a minute. We already saw that one. Oh, no, we didn't. Okay, good. Wait a minute. This is the same video, isn't it? I didn't play that one. There it is.
So let's know first, what do you mean by distance? It is the total length of path covered by object without specifying its direction. Then, what is displacement? It is the overall change in position of an object in a specific direction with the shortest distance traveled. Or let's say in simple terms, it is the shortest distance traveled in specific direction. Still confused? Let's take one example. Let's say I have to go to my friend's birthday party, and his house is 10 kilometers to east from my house. But here I take different and longer route, as I have to buy gift for him, traveling to about 20 kilometers in total. So here, the destination is same, but the path traveled is different. Then, what is the distance and the displacement of the car here? Come, let's see. So, if I travel straight 10 kilometers to east to my destination, it will be the shortest path I can take. Hence, what are we getting here? When I say 10 kilometers to the east, my shortest path. Yes, correct, it's the displacement, but now, as I have to buy gift, I am taking the longest and the indirect route, with no specific direction, but reach the same destination. So, what we get here? When I travel 20 kilometers, with no specific direction, taking the longest and the indirect route. Yes, it is the distance. Now let's say, if I travel 20 kilometers, from one start point, and at the end, stop at the same point, then, what will be my distance, and the displacement? Here, the car starts traveling 20 kilometers from one point, and ends at the same point. The distance traveled here is 20 kilometers. But the displacement is 0, as the starting point and the end point of the car is same, or say, the origin and the destination of the car is the same. Hope you all understood the distance and the displacement. Hit like and subscribe for more such videos.
Okay, so that one was related to the competency dealing with speed. And so with that one, you had to know the term position, you've got to know distance, you've got to know displacement, and also scalar and vector. So a scalar quantity it's a number that doesn't have a direction, and then a vector is a number that does have a direction. Okay, and this next one is dealing with velocity and speed.
We've come to the Porsche Experience Center test track to talk about speed and velocity. And if we're going to do so, we might as well make it interesting. use the terms speed and velocity interchangeably, but in physics, speed and velocity are two very different things. In this segment, we're going to find out how and why this difference matters. The cars speeding behind me are moving with a lot of speed, but what does that mean? Speed is the rate at which an object covers distance. The SI unit for speed is meters per second. It's a scalar quantity, meaning it only has a magnitude. For scalar quantities such as speed, the direction the object is moving in doesn't matter. If the car keeps moving just as fast as it was before, except this time it's going the opposite direction, its speed still remains the same. Just because the car is moving in the opposite direction doesn't mean the speed is negative. Speed will always be a positive value. We calculate the average speed of an object by using this equation. The average speed in meters per second is equal to the total distance traveled in meters divided by the total time taken in seconds. Let's work through an example. When a car makes a lap around the track, we can calculate its average speed using the distance it traveled and how much time it took. One lap around this track is 1,600 meters, and the time it takes this car is 55 seconds. So the average speed was 1,600 meters divided by 55 seconds, which is 29.1 meters per second. That's pretty fast. Okay, we've talked about speed as a scalar quantity. What about velocity? Velocity is a vector quantity. It means it not only has a magnitude, but it also has direction. The SI unit for velocity is also meters per second. So when a car speeds past again, its speed is 71 miles per hour, or 30 meters per second. But its velocity is 30 meters per second going right. Average velocity is an object's change in position, or displacement, over change in time. We can calculate it using this equation. An object's average velocity in meters per second is equal to its change in position, or its displacement, in meters divided by the change in time, in seconds. When solving this problem with velocity, it's important to establish a frame of reference. Let's go to the track for an example. Say that right is the positive direction and left is the negative direction. A car is stationary at our origin point, point A, facing right. It's going to speed towards point B and turn around to stop halfway back to point A at point C. Would the average speed and the average velocity of the car over this journey be the same? Well, there's only one way to find out. It took the car 7 seconds to complete its journey. The total distance it traveled was 24 meters. This means that the average speed was 24 meters divided by 7 seconds, which is 3.43 meters per second. However, the total distance traveled by the car is different from the total displacement. The car's displacement only takes into account the point-to-point difference in meters between the origin and the final destination. The displacement from point A to point C is 8 meters. This means that the average velocity over the journey is positive 8 meters divided by 7 seconds, which is positive 1.14 meters per second, or 1.14 meters per second to the right. So it's possible for the average speed and the average velocity to have two separate values, even for the same journey. To recap, speed is a scalar quantity, which means it has magnitude only. Velocity is a vector quantity, meaning it has both magnitude and direction. But how are we supposed to know which direction is positive and which direction is negative? Good news, it's our choice. We pick our own negative and positive directions. So when you're given a problem to solve, indicate which direction you've picked to be positive. Whatever answer you get should reflect that choice. We usually treat right and up as positive and left and down as negative. So when the car was going from point A to point B, it was traveling the positive direction because we've designated right as the positive direction. If the car went from A to B in 4 seconds, then its average velocity was 4 meters per second going in the positive direction. But when the car was going from point B to point C, it was facing the other way. If it did so in 3 seconds, then it had an average velocity of 2.67 meters per second in the negative direction. Now, let's talk about the difference between average velocity and instantaneous velocity. Average velocity, as we've been discussing, is the displacement divided by the change in time. We calculated the average velocity of the car going from point A to point C. But what about the journey itself? The average velocity tells us the overall velocity over the course of the entire journey. The instantaneous velocity is the velocity of an object at a specific point in time. Let's look at the car as it was starting to accelerate and freeze it right there. At the time 0.5 seconds, its instantaneous velocity is 3.27 meters per second to the right. As the car speeds up, its velocity increases. What if we sped up to right here at 1.5 seconds? Its instantaneous velocity is now 9.81 meters per second to the right. Remember, the instantaneous velocity is the velocity of an object at a specific moment in time. Another important term to know is constant velocity, which is what we call unchanging velocity. Okay, so we've learned what velocity is, whether it's average, instantaneous, or constant. But how do we represent it? If we have a position time graph, we can use it to learn about an object's velocity. In a position time graph, the time elapsed will be shown on the x-axis and its position shown on the y-axis. This graph shows a constant velocity, which on a position time graph looks like a straight line. By looking at the slope of the line in a position time graph, we can learn about an object's velocity. It makes sense that this object is moving at a constant velocity because the slope of the line is not changing. We're covering the same amount of distance in the same amount of time. We can calculate the constant velocity by finding the slope of this line. If the velocity wasn't constant, we can calculate the average velocity by drawing a line between 2 points in time and find out the slope of that line. If we want to know the instantaneous velocity, or our velocity at a given point in time, we can draw a tangent line from that point in time and find the slope of the tangent. We can also have graphs that look like this, with the line going up and down. This point indicates I'm moving in the positive direction away from my origin. This would be me moving at a constant velocity away from my origin in the positive direction. This point right here would indicate me turning around and moving at a constant velocity in the negative direction. It doesn't mean that I'm going any slower or faster. The negative slope just means that I'm moving back toward the origin in the negative direction.
Okay, so I'm gonna go ahead and pause it there. So we kind of talked about like the different terms and what these mean in terms of like position and velocity and speed and all that. But you do have to understand how to read and how to graph those things as well. So if that's not something that you're familiar with, and that's why I chose this video, because the video also shows you what those graphs look like. So for example, this graph is just looking at position versus time, but you also need to know how to graph like speed versus time, or velocity versus time. I think even acceleration versus time. So all of the graphs are going to look different in terms of what, you know, like if I was graphing this position versus time, but I was also looking at speed, my graph would not look like this, right? It would look, it would be going in a different direction. So that's just something that you want to make sure that you on your own go ahead and refresh, okay?
Remember, the slope of a line on a position time graph tells us the velocity of the object. For a more detailed analysis of position time graphs, see Unit 2, Segment D on graphing motion. We've talked about speed and how to calculate the average speed of a journey using distance covered and the time taken. We've talked about the difference between speed and velocity, and the differences between instantaneous velocity, constant velocity, and average velocity. We've also looked at how we can deduce magnitude and the direction of velocity, both average velocity and instantaneous velocity, by looking at the slope of a line on a position time graph. That's it for this segment of Physics in Motion. I've enjoyed myself. I hope you have too, and we'll see you next time.
For more practice problems, lab activities, and note-taking.
So their YouTube channel, they have like a lot of really good videos. I didn't pick them for all of this because I was looking for just like really short ones, but that's one that I would definitely take a look at if you need more help with the physics stuff, with the physics competencies, because they have really good examples, and then they also show you that additional stuff. Some of it may get a little like complicated because they're taking it into like middle school and high school, you know, physics. But I think if you kind of just pay attention to the concepts, it'll be helpful. Okay. All right, so let me find the next one. And this one is going to be related to Newton's laws. So remember that there are 3 laws that you have to know. So Newton's first, second, and third law.
it when a car suddenly veers right around a curve, our bodies seem to lean in the opposite direction. Or when the car suddenly stops, our bodies keep going. Thank goodness for seatbelts. Why does this happen? In a previous video, we learned how things move. Now let's head full throttle into Sir Isaac Newton's 3 laws of motion. That will help us understand why things move. Sir Isaac Newton was born in England in 1642. He's considered one of the most influential physicists of all time. He developed these 3 laws of motion. Engineers need to know these laws to design better safety features in cars. For example, animators and game designers need to know these laws to draw believable cartoons and better games. And you do not want an engineer to build a rocket to launch into space without knowing about Newton's 3 laws of motion. Before we launch into those 3 laws, let me explain a little about forces, because forces are why things move. Say, for example, I push Summer here. She moves. I can pull her too. Forces like a push or a pull can cause us to move. Force is a vector quantity. That means it has magnitude and direction. Okay, so we're gonna arm wrestle now. Okay, we're gonna arm wrestle. It's a great way to show you the difference between balanced and unbalanced forces. If there's an equal push and pull, that's balanced. The forces cancel each other out. You push on my arm, I push on hers. With the same force, there's no movement. That's balanced. If one is greater than the other, Summer's arm pushes more than my arm does, the forces are unbalanced, the object accelerates in the direction of the net force, and Summer wins. Same in a tug of war. If both sides are pulling with equal force, there's no movement. That's balanced. But if one side pulls harder, it's unbalanced, which means there's a greater force on one side than the other. The difference between the greater and weaker force is the net force. I win. Now that you know about balanced and unbalanced forces, let's speed right into Newton's first law of motion. It states, any object at rest will remain at rest unless there's an external unbalanced force that acts on it. In this case, my car is stopped. There are forces acting on me, but they're balanced. That's why I'm not moving. We'll explain more about those forces a little later. Now, once the car takes off, I feel like I'm pinned to the back of my seat because my body at rest wants to stay at rest and resists that forward motion. Newton's first law goes on to say that once an object is in motion, it will remain in motion and will move in a straight line unless there is an external unbalanced force acting on that object. Newton calls this the law of inertia. Inertia is an object's resistance to change. So hit the brakes and my body wants to keep going forward. And the more massive the object, the more inertia it has and the more resistance to change. Let's look at an example. What do you think will happen when a larger person and a smaller person push each other while both are on skateboards? Who moves more? The larger person hardly moves compared to the smaller person. Why is that? Because the larger person has more inertia. He's more resistant to moving. On the other hand, the smaller person is less likely to stay at rest because he has less inertia and is less resistant to change, so he moves more. So remember, objects at rest stay at rest, and objects in motion stay in motion because of inertia, which means they're resistant to the forces acting on them. Okay, so let's say you're in deep space and there are no forces like friction or gravity acting on an object, like this bicycle wheel. How long do you think this wheel will spin? It will spin forever at a constant velocity because of inertia and because there are no outside forces causing it to stop. Which brings us to Newton's second law. Remember these 3 words: mass, force, acceleration. How do these 3 variables interact? Let's use this truck. If I pull the truck, it accelerates. If I pull the truck with twice the amount of force, it will accelerate twice as much. Because force and acceleration are proportional to each other, if you increase the force, then you increase acceleration. The acceleration is always in the direction of the net force. The net force is moving the truck to the right, causing it to also accelerate to the right. Okay, let's double the mass of the truck by adding this weight. How how does that affect acceleration? When I double the weight of the truck and pull it with the same amount of force, it will accelerate half as much. Given the same amount of force, the heavier truck accelerates slower. Now, mass and acceleration are inversely proportional given the same amount of force. You increase the mass and decrease the acceleration when the force stays the same. Okay, here's something about forces you should know. When forces acting on an object are balanced, the object will remain at rest or it will move at a constant velocity. When forces acting on an object are unbalanced, the object will accelerate or decelerate. So when I hit the gas on the car, the force from the tires pushes on the track, causing an unbalanced force on the cart, which causes the cart to accelerate. If the cart is already moving and I push on the gas just enough to move at a constant velocity, then all the forces on the cart are balanced. Forces that could slow the cart include things like air resistance, friction between the tires and the track, along with the friction of all the moving parts of the cart's engine and drivetrain. So if I give it just enough gas to counter those forces, I'll move at a constant velocity because the forces are balanced. If the cart is at rest, then all of the forces acting on it are balanced. So remember, net force equals mass times acceleration. Written, F sub net equals small m times small a. Okay, so let's move on to Newton's third law of motion, which states, for every action, there's an equal yet opposite reaction. That means there are forces at work all around us that we often don't even think about and may even seem counterintuitive. Newton realized that forces work opposite of each other. For example, I walk and my foot pushes on the sidewalk. The sidewalk is pushing back up on my foot. If the sidewalk didn't push back on my foot would go right through the sidewalk. The tires on this go-kart push against the track at the same time the track pushes against the tires, causing it to move forward. These examples are called action-reaction pairs. Anytime an object exerts a force on another object, there is a force equal in magnitude yet opposite in direction back onto the original object. You'll find there's still a lot we're learning every day, and a lot still yet to explore. So get to know Newton's three laws, because they set in motion all kinds of discoveries, like making safer, faster, and more efficient vehicles. Take some time to really understand these three concepts: inertia, net force equals mass times acceleration, and action-reaction pairs. It will definitely help you now and on down the road. And that's it for this segment of Physics in Motion. We'll see you guys next time.
Okay. Right. Okay, so the next one is going to be on simple machines. So again, I mentioned how the simple machines are basically just going to help us do work easier.
Work is the amount of energy required to move an object. The further you move it, the more work is required. Simple machines allow you to do the same work with less effort. Simple machines are all around you. These bikes incorporate 3 simple machines. Welcome to Moo Moo Math and Science and Simple Machines in Real Life. There are 6 simple machines: a lever, an inclined plane, a pulley, a wedge, a screw, and a wheel and axle. If you start looking around you, you will find these simple machines in everyday life. A lever is a long beam with a fulcrum or pivot. The mechanical advantage of the lever depends on the ratio of the lengths of the beam on either sides of the fulcrum. Some common examples would be pulling out nails with pliers, a bottle opener. A shovel is a lever. A golf club is a lever. These cranks on a bicycle, and this wheelbarrow is a lever. And it's also going up an inclined plane. An inclined plane is simply a flat surface raised at an angle. A skateboard ramp is an example of an inclined plane. This motorcycle jump is. And steps are even considered an inclined plane. A pulley is simply a wheel with a groove in it and a rope in the groove, or possibly gears and a chain in the gears. It is used to lift up or lower heavy objects or propel a bike or motorcycle forward. Some examples are gears on a bicycle, This crane uses a pulley to lift objects and lower them, and you will find pulleys on almost every car. A wedge. The main function of a wedge is to change the direction of the input force. For example, if you drive a nail into a board, the nail acts like a wedge and it will redirect this force outward, causing the nail to go into the wood and sometimes will split the wood. Scissors are considered a lever and a wedge. This axe is a wedge. A screw is essentially a long inclined plane wrapped around a shaft. It is used often in everyday life, like this drill. Bolts are a screw. A wheel and axle is basically a wheel mounted to an axle and allows you to transport objects much easier. Bicycles have a wheel and axle. This wheelbarrow does also. If you'd like to know more about simple machines, this playlist will help. And as always, thanks for watching. And Moo Math uploads a new math and science.
Okay, we didn't see this one, right? I think the first video we saw was did we see the changes, chemical changes, physical changes? Or we didn't see that one either? No? Okay.
Have you ever wondered why ice turns into puddles of water on a sweltering day? Keep watching and you'll find out. On Earth, materials exist in one of three main states of matter: solid, liquid, or gas. Materials can change between these states. When a state change occurs, a substance's property will also change. Maybe not too surprising. However, if the state change is reversed, the substance will recover the properties it had to begin with. Neat. Matter can transition between the three states when heated or cooled. But why is heat key in all of this? When a material is heated, it absorbs heat energy. This additional energy can cause attractive forces between molecules to break. This leads to rearrangements of the particles because the attractive forces no longer hold them together as tightly. The same happens when a liquid is heated. The attractive forces between the molecules break, leading them to become more widely dispersed and a gas to form. These four words describe changes in state. Do you know which word refers to which change? Pause the video, fill in the gaps, and click play when you're ready. Did you get them right? Do you know the difference between evaporation and boiling? Both are when a substance transforms from a liquid to a gas. Think of a boiling pan of water, all of the water bubbles. This is because all of the particles have enough energy to become gaseous. But water standing in a pan that is not being heated by anything other than the environment can also turn into a gas. This is evaporation. Only the particles at the surface have enough energy to change from a liquid to a gas. Hence, evaporation is a slower process than boiling, even though it achieves the same state change. Both are types of vaporization. The opposite of these vaporization processes is condensation, the transition from a gas to a liquid. Think of a cold can of soda on a hot day, those water droplets on the outsides, or the dew on the grass in the morning, or the steamed up mirror after a hot bath, even the clouds in the sky, or a foggy windscreen in a car. These are all examples of condensation. Water vapor in the air has cooled down to form liquid droplets of water. Now let's think about the transitions between solids and liquids, so melting and freezing. Think of the Arctic sea ice. In the summer, when air temperatures are warmer, more heat energy is absorbed by the ice. This causes bonds to break between the ice's water molecules and the ice starts to melt. The solid ice becomes liquid water. But in the winter, the air temperatures are colder, and so seawater freezes, and the ice starts to form again. There is less heat energy within the ice, and so more bonds can form, holding it together as solid ice. So far, so good. But did you know that sometimes when solids are heated, they can turn straight into gases? This is called sublimation. This is only demonstrated by particular materials such as solid carbon dioxide, also known as dry ice. When subjected to a certain pressure, it will turn straight into gaseous carbon dioxide. Liquid carbon dioxide does exist, but it only occurs under very high pressures. Similarly, gases can turn straight into solids when cooled. This is called deposition. Let's check out how much you remember about the changes of state. Pause the video and fill in the blanks. Did you remember them all? Our final thing to discover is that when a material changes states, the mass stays the same. The density changes, so the mass per unit volume, but the mass does not change. Our glass of nice cold Coke weighs the same whether the ice is solid or when the ice has melted. So there we have the changes of state. Just remember that the mass stays the same whatever the state.
If you liked the video, give it a thumbs up and don't.
Okay, so notice with that one, how we were talking about phases of matter, solids, liquids, and gases, right? But they talked a lot about energy, right? And so we did do a lot of talking about energy with temperature, and we talked about the different types of energy and how it could be transferred. But when it comes to solids, liquids, and gases, it's the amount of energy that they have that's going to determine like their state of matter, right? Or how it is that they're going to change, how much volume they're taking up. Energy is going to play a factor in that. Okay, we got last two videos. Okay, so with properties, again, it's a way to describe matter, but more importantly, when it comes to like science and doing investigations, it's used to identify substances. So based on them, we can kind of figure out what those are. And so those are some like inquiry activities that you could do with the students to kind of put that into practice. Okay, and then the last video we have is on changes, physical and chemical changes.
No matter where you are or what you are doing, things are changing all around you. Whether it's plants growing, or logs burning, or even if you're just eating food, the materials around you are changing in size, shape, and structure, releasing or absorbing energy, and creating new substances. In chemistry, most changes are divided into two categories: physical changes and chemical changes. A physical change is something that changes the physical properties of an object or substance, like size, shape, or form. Cutting a piece of cloth is an example of a physical change. Even though the cloth changes shape and size when it is cut, it does not create a new substance. It's still cloth. Even if the pieces of cloth are sewn together and made into a shirt, only physical changes have occurred. The shirt is still made of the same substance as the original cloth, just in a new form. Another type of physical change involves changing states of matter, and water is a great example of this. Ice melts and becomes water, and water evaporates to become steam. But no matter its form, the water is still water. One way we can tell this is a physical change is that the change can be undone. Water vapor can condense back into liquid water, and liquid water can be frozen back into ice without changing to a different substance. In fact, many physical changes can be undone. For example, we know that dissolving sugar into water is a physical change, because even though the sugar and the water are mixed together, they do not combine and create a new substance. They are still just sugar and water, and they can be separated from each other. Not all mixtures are as simple to separate as sugar and water. When you mix butter, sugar, flour, and eggs, there is not a practical way to separate them again, but it is still only a physical change. The chemical change occurs when you put your mixture in the oven and add heat. Baking has many of the indications of a chemical change. The mixture in the oven absorbs heat. It also changes color and produces an odor. Gases are released, which is what helps the baked goods to rise. Finally, this change cannot be undone. You can't unbake a cake. Chemical changes occur when the particles of two or more substances are rearranged to form a new substance. For example, when you burn wood, the wood is transformed into a new substance, ash. Just like in baking, this change cannot be undone. Also like the cookies, the wood changes color, releases gases, smoke, and produces an odor. Unlike in baking, this chemical change releases heat and gives off light. Chemical changes take place all around us. Metal rusting, fireworks exploding, fruit ripening, and digesting food are all examples of chemical changes. Here are some clues to look at if you're not sure whether something is a chemical or physical change. Chemical changes always form a new substance. They may absorb or release heat. Sometimes a chemical change will cause a change in color, produce an odor, create a sound, release gases, or produce light. Chemical changes usually cannot be undone. Physical changes do not form a new substance. A physical change may change the shape or size of an object. It may change the state of a substance's matter. Many physical changes can be undone in some way. In a physical change, you end up with the same substance you started with, even if it looks different. I hope you enjoyed learning about physical and chemical changes today. Look around and see if you can identify the physical and chemical changes around you. Goodbye till next time.
Okay, so notice how she mentioned how some of them can be undone, right? So we just want to make sure that we keep that in mind. It doesn't mean that all physical changes can be undone, right? It's just some of them that can, okay? But usually we just want to stick to the fact that whether it is the same thing or not. Okay, so that is going to take us to our time to climb activity. And you're going to go ahead and try a couple of these practice questions. And let's see how you all do.
Virgil, and this is 2 Minute Classroom. If this is your first time seeing my face, welcome. If you like my mustache, you should also like this video, and I'll take it as a personal compliment. Now, on to the topic at hand, the conservation of energy, and energy in general. So, the law of conservation of energy states that in a closed system, that is, a system isolated from its surroundings, the total energy of the system is conserved. Or, more loosely stated, energy cannot be created or destroyed, only transferred or transformed. This is also known as the first law of thermodynamics. So what do I mean by cannot be created or destroyed? If a bomb explodes, it's creating energy, right? And if a ball stops rolling, its energy must have been destroyed. Well, no, because energy cannot be created or destroyed, only transferred or transformed. Let's talk a little bit more about energy. The SI unit for energy is the joule, named after James Prescott Joule, and there are different forms of energy. I'm going to talk about 5. Number 1 is kinetic energy, and is probably the energy you're most familiar with. This is the energy of motion. So any object moving through space has kinetic energy. This includes a ball thrown through the air, a swimming fish, and even a space shuttle flying through space. Number 2 is potential energy. This is the energy that an object has due to its position relative to some reference point. So a book set on a shelf has potential energy. A ball at the top of a hill has potential energy. And in both cases, they have potential energy because it can be easily converted to kinetic energy, right? If the book falls off the bookshelf or the ball rolls down the hill, we're taking that potential energy and converting it to kinetic energy. Number 3 is chemical energy. This is the energy stored in chemical bonds and released through chemical reactions. The bomb example I mentioned earlier is not energy being created, but energy being transformed from chemical energy to thermal energy. Photosynthesis takes solar energy and converts it to chemical energy. So the energy from the sun is literally being stored in chemical bonds within plants, which is pretty sweet. Number 4 is electrical energy. This is the energy due to a separation of charges and flow of electrons, also called an electrical current. All your household appliances use electrical energy and convert it to some other type of energy. For example, your blender converts electrical energy to kinetic energy to spin the blades. Your toaster converts electrical energy to thermal energy to toast your bread. And finally, number 5, thermal energy. So this is the energy given off as heat. When you start a campfire, you're breaking chemical bonds in the wood and transferring the chemical energy of those bonds into thermal energy and fire. Right? Friction is another example. So when a ball is rolling across the ground, there's friction between the ball and the ground. This friction slows the ball down, but it's actually that kinetic energy being transferred into thermal energy, which is then dissipated into the ground. It's also why you can warm up your hands by rubbing them together, because you're taking kinetic energy in the movement of your hands and converting it to thermal energy through the friction. So those are 5 types of energy that you should be familiar with. There are others, but those are the main ones. And all those examples illustrate the law of conservation of energy, which is that energy cannot be created or destroyed, only transferred or transformed. I hope this video helped you and you enjoyed seeing my face. If you're not a subscriber already, please do so now and check out my other videos. And if you have any additional questions, please throw them.
Okay, so what I wanted you all to do, and you may want to, go back through the Nearpod again and kind of refresh yourself with information, maybe watch the videos again. But after you've kind of gone through all this content, is to take a blank sheet of paper and then create a tool. It's called a freeform map. Okay, so what you're going to do is you're going to summarize, again, the key ideas, but you're going to focus on using pictures, symbols, and diagrams, and very minimal words. Okay, and so again, this process, right? So in reviewing today, I had you do some writing. You guys had, you kind of talked a little bit. And so for this last one, all we're really doing is we're just helping you kind of synthesize all that information, right, that you've gotten, because it's a lot of information, and just trying to put it into a picture format. So it's just another way for you to interact with the content to help you understand it a little bit better. Okay, so again, you would just take a blank sheet of paper, and today we went over competencies 1 through 10. So that's what this Nearpod had. I'll be scheduling another review session to go through competencies 11 through 18. So there's still more. There's still a lot more. So it is a lot of content, and like I mentioned, right, there was that one YouTube channel that I would suggest looking into if you needed more help, like with the physics. Each of them have. We kind of talked about physics. We talked a little bit about chemistry. So using the videos that I gave you, I would probably look at like those channels to see if you need more content information. Okay, and so with that, I had this Nearpod code, but I'm going to change it. So you guys already have the new one. So the code that I put in the chat earlier, that one is a self-paced code, and it'll be open for a month. So you can go through it whenever you want. You'll be able to see all the videos, and that way you have the actual content with you. Okay. Did y'all have any questions?